the same thing given by concentration of products divided by concentration of reactants. Now, when you look at those square brackets, they represent the concentration in terms of molar concentration. It is very important to identify that. So whenever you are expressing the concentration in terms of molar, your KEQ can be written as Kc. That's given by the products divided by reactants. So Kc gives you the molar concentration rate, equilibrium constant. So be very careful with that. Now, suppose if I give you an equation, a generic equation. So you have A moles of A, reactant A, then B moles of reactant B at equilibrium. You see the way I write the arrows? Now, these are two arrows. They are different than this arrow. This arrow is for resonance. You will study that in organic chemistry. This is quite different than this arrow. So the one with the two arrows moving back and forth, that is an equilibrium arrow. That means you can isolate your reactant and products. But if you have the resonance arrows, no, you cannot have the two species. Resonance tells you that your real structure is in between your two species. So for example, if I write A and B like that, it actually says that A and B are theoretical structures, right? And the real structure is a hybrid between A and B. That's the resonance arrow. Do not confuse that one with equilibrium arrows. Okay, so if you write equilibrium arrows, if you write this arrow like this in your exam, in place of equilibrium, you're going to get it wrong, right? So just to let you know. So if this is a generic equation, my Kc, if my concentration is expressed in terms of a molar concentration, then my Kc can be given as the concentration of reactants, products, divided by concentration of reactant. And you see the way I have written the stoichiometry, the concentration is raised to the stoichiometry of that particular compound or a reactant or a product. Okay, now what if you are given a reactant and product in a gaseous form? What happens then? Is there any connection between the equilibrium constant in that case? Let's derive that equation. And let me put it in this way. Suppose I have the same equation. Now this time A is in form of gas, B is in form of gas, C is in form of gas, and D is in form of gas. Now, in this case, I cannot write my equilibrium constant in terms of molar concentration. Why? Because these are in a gaseous form. But then the concentration of gaseous reactant are expressed in terms of partial pressure. Now, what do we mean by that? It is the pressure exerted by reactant A that can be given. So if this is reactant A, I will write it to identify A over here. And then how much reactant A I'm using. So that's going to be raised to A like that. So the stoichiometry goes into the exponent like that. Okay, so this would be your partial pressure of A. In the same way, we can write partial pressure of B, C, D, right? And equilibrium constant is given by Kp. Now, P represents that you are dealing with the gaseous reactants and products, and those are in equilibrium. So Kp, just like we wrote for our Kc, I can write it in the same way. This time, is going to be partial pressure of C multiplied by partial pressure of D. Guys, give me a second. I think someone's microphone is. Okay. Okay. So you have partial pressure of C multiplied by partial pressure of D divided by partial pressure of A multiplied by partial pressure of B. Okay. Now, this equation looks quite straightforward. The way we wrote for Kc, you can see it on the left side. It looks like that. Only difference is that here you are expressing your concentration in terms of partial pressure. Okay. Now, can I convert my partial pressures into the molar concentration? Now think about it. Let me give you an ideal gas equation, which you might have seen that before. So PV equals to nRT. All of you agree with that? Do you guys agree with this equation? Have you seen that equation before?
Is the ideal gas equation.
That's an ideal gas equation. Now, here, I will rearrange this equation a little bit. If I write it like P equals to nRT over V, I can do that. Now, let me take two terms a little bit separate. Let's see what happens with that. So I can write P N over V RT. Now, what exactly is N over V? See, N is the number of moles of a particular reactant, and V is volume. Now, if I express my volume in liters, I'm talking about the molarity. Yes, Roberto, you're right. So I'm talking about the concentration. So when I talk of the concentration, I can replace it by the square bracket like this, right? So now I'm going to use the same thing with this equation. I'm going to write down Kp. Now, when you look at slide number 67 to the left, you can see those values, right? So now I'm going to write my partial pressure of C in terms of ideal gas equation. So I can say the number of moles of C divided by volume. And if I raise to the power of C, because that was the partial pressure, but now RT is a constant, that's not changing. So that's also raised to the power of C, multiplied by my next reactant, ND, right? So the number of moles of D divided by volume, multiplied by RT raised to D. And this also has to go to the power of D. And I can divide it by NA over V, which is the volume, and then RT raised to A multiplied by NB over V, RT raised to B. Now, I can simply replace this by the square bracket. What does it mean? This one is the concentration of C, and then multiplied by RT raised to C. And this one, the next one is concentration of D, RT raised to D, divided by concentration of A, RT raised to A, and concentration of B, RT raised to B. So far, so good? Simple math?
So far, so good.
Okay. So now let's see. I will keep all my concentration terms on one side and see what happens. So concentration of C, concentration of D, divided by concentration of A, concentration of B. And the next part I'm going to say, this is RT raised to C plus D, because that's the constant, and I can say RT raised to A plus B. Isn't it that this part is your Kc? So I'm going to write it as Kc. And now I can write my RT terms when I solve this exponent, essentially what it means is C plus D minus A plus B. Now, what does it mean? The total number of moles on the reactant side minus the total number of moles on the product side. That's what it means. So essentially, we are looking at the change in number of moles when you go from reactant to the product side. That's what you are looking at. So I can say Kc is RT raised to delta N. Delta N equals to change in number of moles. So this is the equation, classic equation, how to convert your Kc, Kp into Kc and other way around. So far, so good? Any doubts so far before I go to the next topic? If not, let me paste one problem. And I believe you might have seen those problems in your slides and in your videos. So here is a problem taken directly from your book. As you can see, we have 4 experiments and we have the initial concentration. So this reaction, I can write it down for you. So you're going from N2O4 to NO2. That's basically the reaction that you're looking at. So it's a decomposition reaction. Let me write down on the top. So N2O4 is a colorless gas. When it decomposes at a higher temperatures, it will give you NO2 gas. NO2 gas is a brown color gas. So this is the reaction that is happening. Now, for my experiment number 1, see what I'm saying. I'm saying my initial, like a concentration 0, because that's where I'm starting at. But then I have my initial concentration of NO2 gas, which is this one. At equilibrium, I'm seeing these two values, and I'm getting the Kc value like this. Now, your exercise number 1, find me Kp for one of these experiments. So let's select experiment number 2 and experiment number 4. Find me Kp for, yes, Kp, because here you are given concentration in molar terms. So find me Kp for these 2 reactions, since you are already given that equation. I'll give you 2 minutes to do that. And if you want, I can give you the value of R. In this case, 0.082 liters atmospheres per mole per Kelvin. This is the value of R that you are going to use.
Professor, what would be A, B, C, and D? It would be these 4 molar concentrations that you're giving us?
Okay, so here we simply have one reactant and one product. So the stoichiometry is 1, and for NO2 is 2. So let me write down that equation for you first. So Kp, here we are given Kc. Your products, which is NO2 raised to 2 divided by N2O4, that is what is given to you. And it looks like from the data, let me see what is happening here. So initial is 0, it goes from here to here. Yeah, so that looks good. The data looks good. Okay. So this is given to you, and you are given the equation of Kp and Kc.
Can you go back
KC
to
is,
the other slide?
you can see on the left side.
Can you expand it a little bit?
Now for this one, you probably do not need to use the expanded version. Just like this, you don't need that. You can simply take this equation and get to the answer. Give me some number for KP.
Professor, what would be the units for KC?
KC, what do you think should be? In this case, what do you think should be the units? See, your NO2 in this case is expressed in molar concentration, but then you have two NO2s. So molar square divided by N2O4 is in molar. What do you think should be the units?
Just molar.
Absolutely. Very good. Let me see. That looks like correct to me, Roberto. So one answer for the first one is 6.45 atmospheres. The second one is 6.51 atmospheres. That looks correct to me. That looks correct. So you'll be using equation Kp equals to Kc or T raised to delta N. Now look at the number of moles that are being changed. So delta N in this case, you have 2 moles on the right, 1 mole on the left. So you are looking at 2 minus 1. So you are looking at delta N equals to 1. So in this equation, you have delta N equals to 1. What is Kc? 0.211. And this is per molar multiplied by, I'll just move everything to the right side or left side. So I have enough space to write. And then R is 0.082 liters atmospheres per mole per Kelvin multiplied by temperature. See, the temperature in this case is 100 degrees centigrade. So 373 Kelvins. So Kelvin and Kelvin will cancel out. And look at this one. Liters per mole is essentially, we are saying, see, moles per liter equals to molar. If I invert it, that is per molar. So I can simply write 0.211 molar, and I'm adjusting the units at this time only, 82, and atmospheres per molar per Kelvin multiplied by 373 Kelvin. So Kelvin and Kelvin will cancel out, per molar and molar will cancel out. You will be remaining with atmospheres. And what do we have here? Okay, so that one would be, let me see what we got. 6.45 atmospheres. That looks correct to me. All of you got that one?
No,
You get different answer?
no, I think I didn't understand how to get KC.
KC is given to you. It's right here in the table. KC is given to you.
So you're just doing it for experiment 2?
Yeah, so the one in a green. So for 2, we are using KC 0.211. For 4, we are using 0.213.
Did we use both in this equation or just one of them?
No, only one by one, because we are finding
Oh.
it individually. Yeah, exactly. So
Okay, got it.
if I write down here, so when you find KP for 211, you found 6.45 atmospheres. And for 0.213, you found 6.51 atmospheres. Okay, now interesting thing, you can see for various experiments, you can see over here, for various initial concentration and the final concentration, you can see at equilibrium, they tend to be nearly the same. And that's why Kp is also same and Kc is also same. That's the reason why we call it an equilibrium constant. Now, let me ask you a question. At 100 degrees centigrades, right? At 100 degrees centigrades, if I write my Kc, now I'm focusing on Kc only, right? Just think about that. My Kc is given as NO2 and N2O4. Okay, can you tell me what does it mean? See, my Kc is less than 1. What does it mean? In terms of the concentration of NO2 at equilibrium. Understand in terms of concept. Look at these values. Does it give you the direction of equilibrium? See, we started with this equation, right? Where we thought that N2O4 is decomposing into NO2, right? That's what we thought. Look at these numbers and tell me what you see. Do these numbers make sense in terms of equilibrium? Let me write down one more time here. This is the way we wrote down that equation. Initially. Now, does the data support this equilibrium? What do you guys think?
Professor, I don't think I'm understanding what you're saying.
Okay. So this is the equilibrium that we started with, right? This equation.
Yes.
Does the data which is given to us and equilibrium constant that is given to us, does it support the way I have written this equation in this form, or does it support this equilibrium? Which one does it support? Now they may look quite similar. I just changed my reactant on both the sides. I inverted my reaction. So which one of them is correct based on the data? So what I will do is I will give you 2 minutes to think about it. 2 minutes. You are going to write down the private chat message to me on Zoom. And if your answer is correct, you will get extra 2 credits added directly to your next exam. Think about it. Does the data support A or does it support B? I will give you 2 minutes. It's 8:32, 8:34 would be the fine point. And also you need to explain, why do you think that that data supports A or B? What is in the data which supports either A or B? Okay. I'm getting the answers. I'll give you 1 more minute. What is in the data? Okay. Let's see. Guys, I need, let's see, so far I just received a couple of responses. I would be glad to see more. Okay, and why is that? So A, you need to explain, and if it's B, you need to explain in the chat, the direct message to me on that. Okay, so guys, the time is up. So I'll just mention here. Okay, so the time is up for the extra credit. Now, look at the data that's given to you. If you plug in the values for NO2 and N2O4, the data supports which one? Let me see what we have here. So data supports, okay, I can see I can see 3 responses. Okay. So data supports A. Let's see if it does, right? Let's just put those numbers in that. So Kc equals to my reactant concentration, my product concentration, the way I have written that equation, square divided by N2O4. And if I just simply put in those values at equilibrium, so NO2 is 0.0172. And if I square it, and N2O4 is 0.00140, what do you get? Are you guys getting the answer 0.211 molar? Yes, so you're getting that. So data does support A, the way I had written that equation. Okay, but then see one interesting thing here. This tells you that you have the reactant. You can see how much reactant do we have at equilibrium. What can you tell me about that? Is your reaction favoring the forward reaction, or is it favoring the reverse reaction? What do you think about that?
Is the forward reaction.
It's the
'Cause there's
forward
more
reaction.
the product.
Okay, but then if it is favoring the forward reaction, isn't it that Kc is less than 1? So how is it supporting the forward reaction? That is kind of strange, right? So how can we have two things at the same time? Think about it. See, that's the reason why I gave you this problem. Now, what do I mean by that? See, the moment you have Kc, which is less than 1, which means it's a fraction, your forward reaction is not favored. That means your amount of product is less than the amount of reactant. That is when you're going to see Kc less than 1. If Kc is more than 1, that's when the product are favored. But in this case, what we just said was Kc is less than 1. So what do we mean by that? Why is it that the way I have written gives me something counterintuitive?
Doesn't that just come down to like how little concentration there is of both?
How little concentration is? So can you expand on that?
Like the numbers themselves are way too small for it to give you anything above 1.
Numbers are small. Okay, that's true. But then in any given equation, okay, let me give you that perspective. Let me go over here. Now, when you multiply these two small numbers, so you are squaring it, and that's why you think that's going to be less than that. Now, when you look at the value over here, what would be the square of this? Can you tell me that amount, that number? Because I'm just going to prove.
Repeat the question because I was looking away for a second.
Okay, so if you square 0.0172, what would you get? So if you square the small number, yes, you're going to get a smaller number than that. But now here, that number is in molar square. So we cannot compare apples and oranges. You see what I'm saying, right? So what you mentioned was if I square this one, I'm going to get a smaller number than that. And that's why Kc is small. What I'm saying is in terms of real concentration, there is a problem. In terms of real concentration, if Kc is less than 1, this value should be more than this one. But then we are seeing the other way around. So if it is the other way around, what exactly is going on with this equation? So this tells you that your reverse reaction is favored. And how do we know that? Let me put the reverse reaction and see what happens with that. If I write it as Kc, this is for the reverse reaction. Can you find me the Kc for this reaction? We're using the same numbers, the one which you had. Are you guys getting 4.7 something? $4.73. Exactly. So this number gives you 4.73. So you have to follow the Kc number, the equilibrium constant. If it is greater than 1, then your products are favored. If it is less than 1, your reactants are favored. In that sense, I can say at 100 degrees centigrade, your reactants are favored, not the products. So if I were to do this reaction at 100 degrees centigrade, most of my reactants will stay as it is. So let me give you this table. This is taken directly from your book. So you will be able to identify in the slides. So if your K, which is equilibrium constant, if it's more than 1, then you have more products than the reactants. If it is less than 1, you have less products than the reactants. Okay, so you need to know about this one. Now, in terms of experiment, what exactly is going on? So let's see. If this was my round bottom flask, and if I had the two reactants A and B reacting together, or if I just say my A decomposing into B and it's an equilibrium. Now, at a certain point, if I take the sample of this mixture, I will also see A, I will also see B. I will see both of these species in my reactor, right? But then the ratio between A and B will be decided by equilibrium constant. So if equilibrium constant is more than 1, I will see way more B than A. If my equilibrium constant is less than 1, I'm going to see way more A than B, right? So both of them will be there. Now, if my equilibrium constant is ridiculously high, very, very high number, very big number, then my B is going to predominate my reaction mixture. I'll see a tiny amount of A, and that's where we want our reaction to be. In general, if I'm doing a particular reaction in the lab, I want my reactant A to go to B. I do not want my unreacted A over there. So I want my equilibrium constant to lie to the right side, to the product side, than the reactant side. And I want my K value to be way more than for the reverse reaction. Okay. Given that, let's see one interesting example. What if you are given multiple reactions, multiple equilibriums? I will give you a generic equation over here, and then we'll solve one problem on these two. So suppose if I have a reactant A reacts with B at equilibrium gives you C. Or I can just say an intermediate. I'll just write it as A to B. This is an intermediate. And suppose equilibrium constant for the step number 1 is K1. Now A to B, which is my intermediate, undergoes decomposition or rearrangement, and it gives me product C. Equilibrium constant is given by K2, right? What would be the overall equilibrium? What do I mean by that? I start with my first reaction. I get to my intermediate. I'll just write I as an intermediate. And then I get to my product, which is P. This is K1. This is K2. So this is an equilibrium with intermediate. Intermediate is an equilibrium with the product. I want to know what is the overall equilibrium constant for this. How do I know that? Quite simple. Let me write down here. Let me go on the next slide. Or rather, let me copy this one so that you will be able to see this. Okay. Now, suppose if I add these two reactions, what would I get? Simply 2A plus B plus A2B. This should be my overall equilibrium, which I'm looking at. So I will just put it as K as overall equilibrium. And that's giving me A2B plus C. Now, I can cancel out the common terms on reactant and the product side. So A to B is common. Essentially, what I'm looking at is 2A plus B at equilibrium with C. So far, so good? Are you guys there, or am I the only one in the room? Okay, you guys are here.
Professor.
Okay. Okay. So I can write K based on my last equilibrium, which is the products divided by the reactant. Now, how about if I multiply both the sides, the top and the bottom, by A to B, what happens then? Let's see. It's not going to change anything because I'm multiplying and dividing by the same term. So it's not going to change anything. Well, now see what I'm doing. I'm going to bring A to B like this, and I can have A to B on a separate way in this, and both of them are multiplied. I'm just rearranging this equation. So this is multiplication. Okay, so I get that one. Now, do you know what these are? What this is and what this one is? These two terms? Let me go back on the first equation. So if I have to write K1 for the first equilibrium, that's going to be A to B concentration divided by concentration of A, concentration of B. And if I want to write K2, that's going to be concentration of C divided by concentration of A to B. Well, it looks like I have K1. So this is K1 and this one is K2. So my overall equation K is multiplication of equilibrium constant 1 multiplied by equilibrium constant 2. So I got these two together. So you should be able.
Back a slide, Professor.
Yes, sure, I'll do that. So let me give you one example of this. Are you guys done writing this?
Yes.
Okay. Now, suppose if you have an equation, I will give you those numbers. I'll take this slide, I'll copy this one. Now, suppose for the first one, the equilibrium constant, I'll give you those numbers. That's going to be 0.014 per molar. And for the second one, it is, say, for example, 7.2. In this case, you don't have any units because you have molar on the left, molar on the right for the second one, so they will cancel out. Can you find me the overall equilibrium constant for this reaction? So K will be K1 multiplied by K2. What do you think that one is? So 0.1008. Okay. Okay, and also the units are correct, Roberto. Good. Okay, so that would be the way to solve the equilibrium, the final equilibrium if you have multiple equilibriums linked together. Okay, so let's see one more example. This is for Kc and Kp. If you are given sulfur dioxide gas, and that reacts with oxygen in gaseous form at equilibrium, you have sulfur trioxide gas that's given to you. Suppose if I give you temperature as 800 Kelvin, and suppose the initial concentration, see the way I'm writing the concentration, suppose the initial concentration, not initial, that at equilibrium concentration of sulfur trioxide is 10 to the power -2 molar. Suppose the concentration at equilibrium for sulfur dioxide, that's 3.0 10 to the power -3 molar, and concentration of oxygen is suppose 3.5 10 to the power -3 molar. So when I take the sample of my reaction mixture, what I'm seeing at equilibrium at 800 kelvins, I'm seeing sulfur trioxide 5 10 to the power -2 molar, SO2 sulfur dioxide 3 10 to the power -3, and oxygen 3.5. What you need to find is Kp and Kc, and I will give you the value of R, that's 0.082 per molar per Kelvin, and I'll just write atmospheres here. So I'll give you 2 minutes to do that. Should be really fast now. And before you do that, be very careful. Look at the equation. Does it make sense? Then plug in those numbers. If it doesn't make sense, you need to fix this equation. If you don't fix that equation, you won't get the correct answer. So can I use this equation in the current form, guys?
You have to put a 2 before the like
Very
sulfur
good.
oxide, dioxide, and sulfur trioxide.
Very good. So we need to balance this equation before we use the equilibrium equation. So I'm not sure why it's not letting me do that. Okay. So now when I write my Kc, because we have been provided the molar concentration, so we need to use Kc over here. So Kc will be the concentration of my products, sulfur trioxide, but I need to put the coefficient on the top from the balanced equation, and sulfur dioxide and concentration of oxygen. Now, I've been provided with all three of them, right? So when you look at SO3 concentration, it's 5 10 to the power -2. So this is square. And then for sulfur dioxide, that's given to me as 3.0 10 to the power -3, again square. And then we have 3.5 10 to the power -3. Can you give me this answer? See, guys, I'm getting 0.79 10 to the power 5 per molar. Are you guys getting that answer?
Can you repeat it, Professor?
I'm getting 0.79 10 to the power 5 molar.
To which power you said?
For this one, for the Kc,
No, but like what power did you say again?
10 to the
I'm
power
saying-
5. Yeah, 10 to the power 5.
Okay.
Are you also getting that same answer? Okay, so it's essentially the same thing. So 0. Okay, so you guys are getting the same answer. So if you put it in the sig-fig form, that's going to be 7.9 10 to the power 4 or 0.79 10 to the power 5. So you guys are right, 7.93 10 to the power 4 per molar. That's basically the equilibrium. Now, this number, you can see it's a huge number, right? So what does it tell you? Where is the equilibrium? It's basically on the right side. So when you take the sample of this compound, of your reaction mixture, you are going to see a lot of sulfur trioxide because equilibrium constant is really, really big number. So it is favoring the formation of your product, right? The amount of reactant is really small, as you can see in the numbers as well. So here we found the equilibrium constant from these numbers. But now if I just simply give you this equilibrium constant without those concentration, just by looking at this number, you can tell me that equilibrium favors the product. It is more towards the product side than on the reactant side. Okay, given that, can you calculate Kp for me now? You found Kc, now find Kp. And for this one, you should be using the equation Kp equals to Kc or T raised to delta N. So you already found Kc. You know what R is. You know what T is. It's 800 kelvins. And you know what delta N is in this case. Can you check the exponent one more time?
-1.
The delta N in this case, think about that. So in the balanced equation, look at the number of product molecules. So you have 2, and then on the reactant side, you have 3. So 2 minus 3 is -1. So delta N in this case is -1. So C plus D, which is the number of moles on the product side, in this case is 2 because you have 2 sulfur trioxides. And on the left side, you have 2 sulfur dioxide and 1 oxygen. So delta N equals to -1. Now, can you find me this number?
Pastor, I have a question about like the units of Kp in general.
Mhm.
Um, would it always be a variation of like atmosphere?
Yes, because we are expressing our concentration in atmospheres. Because we are explaining, so we are giving it in form of the partial pressure of gases.
But can it still be like a negative exponent of atmosphere, like inverse atmosphere?
Yes, 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 absolutely. So in this case, you're going to get a negative exponent. So atmosphere -1, that's going to be your units for that, Kp. So just like in Kc, you had per molar, in Kp, you should have per atmospheres. That looks correct, Roberto. So it's 1209 per atmospheres. Very good. 209 per atmospheres. Good. So now you can see we got a huge number in terms of Kp value as well, right? Okay. So this also tells us that the equilibrium favors the product, right? Okay. How about solving one more problem? So you are given N-butane, right? So I'll just give you a structure of N-butane. This is how it's going to look like. This is N-butane. At equilibrium, it is giving you, I'll just put it here as an isobutane. So this is the structure of isobutane. It's just a rearrangement. And let me put where the carbon is. So on those red dots, we have carbons. And each carbon can form 4 bonds. So if you do not see 4 bonds, that means you have hydrogens on them. So essentially what I'm saying is you have 3 hydrogens over here. This is the way we write it in organic chemistry. We don't write hydrogens in the line angle formula. So this is what is happening. It's a simple rearrangement. Now, can you find me the Kp and Kc value for this one? Find me Kc and then find me Kp for this. And I'll give you 2 minutes to do that. So in this case, I have isobutane as the product and N-butane as the reactant. So I will say I, which is for isobutane. So I will write the formula C4H10. That's the formula. And then the concentration of N, that is N-butane, and it's the way to write it in organic chemistry. C4H10. Are you given the concentration, equilibrium concentration of isobutane? Answer is yes. Are you given for N-butane? Answer is yes. So can you find me this value? .875. All of you are getting that same answer. Because I'm getting something different. Yes. So I'm getting 2.6 or 2.56 is also correct. So 2.6, I will just keep it at 2.6. Now, in this case, Kc has no units. Why? Because the concentration of the top is molar, concentration of bottom is in molar, so that will cancel out. This is the number. Now, what would be your Kc in this case? See, Kp. So Kp equals to Kc RT raised to delta N. But see, I have not given you the temperature over here. Even if I have not, so here I given you room temperature, but I didn't give you that number. What exactly is that number, right? But understand this. Do I need number for this one, for this equation? Answer is no. Why? Because your delta N is one molecule or one mole on the reactants product side minus one on the reactant side. So delta N is 0. Anything raised to 0 is 1. I don't need the value for R. I don't need the value of T. In that sense, I can simply say Kc RT raised to 0. Anything raised to 0 is 1. So Kp equals to Kc. In that sense, I can simply write my Kp equals to 2.6. So Kp and Kc are same in this reaction.
What would be the units of Kp in this case?
No units, just like we don't have any units for, just like we don't have any units for Kc, we don't have any units for Kp. Make sense?
Yeah. Yes.
Okay, so let me expand this. So I know that since this came up, I'll just put those values. So suppose if it's Kc, the value that we are putting here is 0.041 molar. if this cancels out, so based on this, you found that value, right? 2.6. Now, since this cancels out, if you try to convert your molar concentration into atmospheres, you would have seen atmospheres on the top as well as on the bottom, and they should have canceled out. So if you were given the partial pressure, that would have canceled out as well. So the best way to know the units for your Kp and Kc, if your units for Kc is, I'll just write down here. If Kc unit is per molar, your Kp would be per atmospheres. If Kc is per molar square, Kp would be atmosphere square. In the same way, if Kc has no units, Kp will not have any units. So you just need to convert this one into atmospheres, this one into atmosphere. Exponent stays the same. So far, so good?
Yes.
Okay, let's solve one more problem. Now this problem is quite interesting because so far I was giving you the values for the reactants and products at equilibrium. That means we start the reaction and we reach equilibrium and we analyze the reactants and products and we find the equilibrium constant. Okay, this time we are going to do something else. How about you are given the sample of nitrosyl chloride, NaCl, and this decomposes into NO, which is nitric oxide, and chlorine gas. Well, how does that equation look like? NaCl, that's a decomposition reaction, and this is going to give you NO plus Cl2. And all of them are in gases. So how would you go about this problem? What should be your starting point? See, we start with a starting point. What should be my starting point? Balance the chemical equation. How do you do that? Guys, can you balance it for me?
2 NOs and 2 NOCLs.
Very good. So I'm going to put 2 NOCl, 2 NO. My equation is balanced. Now let's see what is given to us. Well, we are given 1 mole of sample of NOCl in 2 liters. See, this is getting interesting. 1 mole in 2 liters. So we are given the reactor size, 2 liters. We are given temperature, 227 degrees centigrade. Well, we are given that one as well. And we are given equilibrium concentration, which is 0.056 molar of Cl2 at equilibrium. Can you calculate K, which is in this case, what do you think is K? Am I referring to Kp or am I referring to Kc? Which K am I referring to? What
Kc.
exactly? Kc. How did you get to that point? You are right. It is Kc. But then how?
gas.
But then for the gas, we write Kp, right?
Yeah.
But then in this case, if I told you that you are given the molar concentration, can you spot it? Where is the molar concentration? I can tell you, you are given the molar concentration of nitrosyl chloride, NaCl. You are given that.
1 mole divided by 2 liters.
Very good. Wonderful. So basically, you have 1 mole divided by 2 liters. That essentially means you are given 0.5 molar solution in that sense, not in the sense of what we are thinking, right? But then since we are looking at a gas. So let me put one slide above so that you can see what I'm saying. So what Roberto said, all of you, we are given N equals to 1 mole. That's given to us, 1 mole of NaOCl. We are given volume, which is 2 liters. If you find the molarity, isn't it? It's the moles per liter. That's the molarity, right? So if you are given 1 mole of NaOCl divided by 2 liters, we already got moles per liter. And what is moles per liter? That's the molar solution. So here we have 0.5 molar gaseous solution of NaOCl. Well, that's good. That's good. So now think about it. Just give me a second, guys. Okay. Now think about it. My initial concentration of NaOCl is given to me. That one is 0.5 molar. That's given to me. But then when I just started my reaction, was there any NO or Cl2 in the reaction? No, there was no, because I just started it, right? There was no NO or Cl. So I'll put it as dashes, right? Okay. Now, at equilibrium, I'll put it here. How much Cl2 is there in terms of moles? 0.056. Can you tell me the concentration of Cl2 at equilibrium? So E stands for equilibrium. So I stands for initial, E stands for equilibrium. Let's see what we have. Very good. So at equilibrium, we have 0.028 molar solution of chlorine. Very good. Now, based on this, look at the ratio. For 1 mole of chlorine, you will always have twice the amount of NO. So can you tell me, at equilibrium, if I'm having 0.028 molar Cl2, how much NO is there? Very good, 0.056. 0.056 molar. So we got the amount of NO at equilibrium. Well, now the thing is, how much NaOCl is there at equilibrium? Be careful. This one, look at the ratio between NaOCl and NO. It is 2 to 2. It's an equal amount on NaOCl and NO, right? I mean, when I say equal amount, that means the molar ratio should be the same. So if I have 0.056 molar NO, isn't it that I used 0.056 NaOCl because that's the amount that got converted into NO? Would it be the same amount? So at equilibrium, how much will that be? How much will this number be? 0.444. Very good. So now what I'm going to say, before I do that math, I'm going to find the change. So I just generated 0.056 molar in my reactor. This one is also 0.028 molar. That was the change from 0 to 0.028, from 0 to 0.056. And this was the amount that was used in this reaction. So why did I select this number? Because the stoichiometry of NO and NaOCl is the same. So I used that number. But then why did I use negative sign? Because I used that amount of NaOCl to get NO. Okay. Now, when you add these two things together, you are going to get a change, which is 0.444 molar is remaining back. And you can see we call this as ice table. Okay. Now I got the equilibrium concentration for all three of my species. Now I'm going to write down K, C in this case, the concentration of my products divided by concentration of my reactants. My products are already given to me 0.056 square, and then for chlorine 0.028, and then for NaCl 0.444 square. And when I look at the units, it's going to be molar. Okay, can you find me this number? Four 4.45, 10 to the power, let me see what you guys got, 10 to the power -4. Okay, that looks correct to me. Okay, so 4.45, 10 to the power -4 molar. Now, what does it tell you? It tells you that this Kc, equilibrium constant value, is small. That means at equilibrium, you should be seeing more of your reactant than the product. Equilibrium is favoring your reactant rather than the product, right? This also tells you in terms of the stability of your reactants and product. It tells you that reactant do not want to go on the product side. It wants to stay as a reactant. Conceptually, what does it mean? It means that your reactants, the bonds in your reactants are way more stable than the bonds in your products. That's why your reactant do not want to go on the product side, right? There is no incentive for reaction to go on the product side, right? So this K value, it's not simply a value, it gives you the information about the stability of your compound or your reactant in the products. Okay, now can you convert this into Kp? You know the formula. Can you find me Kp value for this? And you are given temperature, 227 degrees centigrade. Now be very careful. Do not use degrees centigrades. We always use Kelvins in these calculations. You need to convert this into Kelvins. So 0 degrees centigrade is 273.15 Kelvins. So think about that. Use the temperature in form of Kelvins. I'll give you 2 minutes to do that. Okay, guys, can you hear me?
Yes,
Yeah.
Professor.
Actually, I was thinking, okay, I thought that I was, all of you were listening, but then I was on mute and I was talking. Okay, so the value is 0.0. Yes, you're right, George. So the value is 0.083, 0.0183 atmospheres. So as you can see, if you have the concentration expressed in molar, your concentration in Kp would be atmospheres. Okay, now let me give you one more interesting thing. If you had seen those videos, there was a principle which we call Le Chatelier's principle. Do you guys know about that principle? Le Chatelier's principle. Did you see that one? So I'll just write here what that Le Chatelier's principle is. Is an exact verbatim by Le Chatelier's. Okay, so this tells you that if you have a reaction at equilibrium, right, and if you try to disturb it, when I say disturb it in sense of trying to change the concentration, trying to change the pressure, which is effectively the concentration, trying to change the temperature, again, you're trying to like disturb a reaction. If you are trying to do any of those, there will be the change in the direction of equilibrium. Now, what do I mean by that? Let's take an example. Suppose at equilibrium. So think about equilibrium as a seesaw, right? Suppose at equilibrium, you should have 50 kilograms on left, suppose, and if you have, let's say, 40 kilograms on right. Suppose we have that kind of equilibrium. So what would be the ratio? So let me, instead of doing that, since we have exactly in the center, I will just keep it at 50-50, right? So suppose I have weights, which are 50 kilograms on left, 50 on the right at equilibrium. Everything is balanced. Now, if I add from outside 10 kilograms on the right side, what would you expect? What would be the first thing that should happen? You put 10 kilograms on the right side. What should happen?
We'll shift to the right
The
side.
left side will go up.
Exactly, the left side will go up. So this is still 50 kilograms. This is now 60 kilograms. Now, to gain the equilibrium back, which is 1-to-1, I need to transfer some of my weight, which is on the right side, to the left side. How much weight should I transfer on the left side so that it's equal on both the sides?
5.
5, exactly. So I'll just move it here. So now I'm going to transfer 5 kilograms to the right side. And when I do that, I regain my equilibrium. Only thing is, now I got 55 kilograms on the left and 55 kilograms on the right. Now, did you see what happened? Think about this as the reactant and think about this as product. When I externally add product from outside, I'm increasing the concentration of product. To regain the equilibrium back, since I disturbed this equilibrium, I just moved it down. I'm going to shift some of my product on the reactant side. So now I'm seeing more of the product coming out. So depends on which side you are affecting. So if you are affecting the product side, the equilibrium will shift to the reactant side. If you are increasing the weight on the reactant side, you are going to shift the equilibrium to the product side. Now, let me put one more example here. suppose if I remove 5 kilograms, or say, for example, not 5, let me remove 10 kilograms from the right side, what should happen now?
Left side will give over 5.
Exactly. So now my new position will be 50 kilograms here and 40 over here. To gain back the equilibrium, I need to transfer 5 kilograms on the right side. So now I got 45 and 45. Did you see what just happened? When I remove my product from the system, I'm shifting the equilibrium to the right side. Now I'm converting more of the reactants to the products, right? So in short, when you think about the concentration, when you increase the concentration of reactant, you move the equilibrium to the right side. When you increase the concentration of product, you move the equilibrium to the left side. When you remove the product from the system, you are moving the equilibrium to the right side. That means to the product. So more product will be formed if you keep on taking out your product. Okay, so this principle is called Le Chatelier's principle, and we use this principle a lot. In fact, many industries, in fact, most of them will account for this. So for example, esterification reaction. Let me show you that equation. So I'm just giving a simple example. So acetic acid reacts with ethanol, and it's an equilibrium reaction, and it gives you ethyl acetate and water. Now, this reaction is at equilibrium, right? That means you can only go so far to form ethyl acetate, the product. Why? Because now you're also converting your ethyl acetate back into your reactant. So what do we do in industry? We will keep on taking out water from the system. If I remove one of the products, what's going to happen? More and more my reactant will get into that. This is the practical application of Le Chatelier's principle. The second thing, let me give you one more example. This is the reaction between ammonia, between nitrogen and hydrogen, giving you ammonia, right? Now, in this case, all are gaseous reactant. Now, this reaction is an exothermic reaction. Delta H is negative in this case. So heat is given out. Heat is one of the products. So if I heat this reaction, what will happen? The equilibrium will shift to the left side. The reaction do not want to go forward, right? So depending upon where your reactants are, if you increase the concentration of reactants, right, you are going to move the equilibrium. The same thing goes for the products as well. Okay. Now, given that, let me go through one more concept, the concept of reaction quotient. But then we are going to solve a problem directly using that so that you'll learn more through that one. Now, before I go to Q, what exactly is that? Let me give you the equation of Q. This is for this equation. It is the same thing as the concentration of my products divided by the concentration of my reactants. Now, the thing is, you would wonder if it looks like the same as equilibrium constant, so what is the difference? At equilibrium, so once you achieve the equilibrium, that's the constant value. This is the ratio of reactant and product for the reaction which has not reached equilibrium so far. So you start the reaction and you observe it over the time until it reaches the equilibrium. It's just like your seesaw moving back and forth until it gains that equilibrium position, right? So until it gains that position, that ratio between the reactant and product is given by Q, right? So can you calculate Q for me? First of all, do that. So this is given to you. So can you first calculate Q for me based on the data? Okay. Now, do you think it is 4 molar or just 4? Because you have molar on the top and molar at the bottom. That's right. Very good. So your Q in this case is 4. Now, this Q will tell you whether you are going to form more products or less products. So we are going to go through that in the next class. And before you guys leave, I have some, give me a second. For the next class, the announcement is that go through the videos that have been provided to you for chapter number 16, which is acids and bases. So I'll just put it here. So now you have that information. So there are 6 videos, and you also have one video in that. Now, do you see all the material for acids and bases in front of you?
Professor, if you're sharing something, we're still on the PowerPoint.
I'm sorry?
I see the assignment.
Okay, you see the assignment, and also just check it out. So basically, besides that assignment, that video 6, you have, okay, let me share my screen so that you know what I'm talking about. Do you
We
see
also
my screen?
Field 7, right?
Yes. So these are the videos that you should be watching. You have 6 videos. You should be completing video number 6 before coming to the next class. So just let you know about that. Let me see what I have.
Professor, each video is an hour?
I'm
Like
not sure. Some of them are big videos, but then yes. So that's what you need to do before coming to the class next week. Okay, guys. So let me know if you have any question.